Yo, real talk. There's a machine straight up ghosting through the pitch black void between stars right this second. Humans built this thing with their own two hands back in the 70s. It's rocking a computer weaker than the calculator sitting in your junk drawer. Its power source is dying out, bleeding exactly 4 watts every single year, no cap. And ain't nobody able to pull up and fix it because it's over 15 billion miles from Earth. And the signal it sends back home, that faint little whisper crossing that insane distance, takes 23 hours to reach anybody on this planet. This ain't some sci-fi movie plot. This is Voyager 1. And its last chapter has already started. Nobody's told the whole story. That's the first thing you gotta understand before any of this makes sense. The version everybody already knows. Spacecraft got launched, flew past a couple planets, snapped some pics, disappeared into space. That's technically true, sure, but it skips literally everything that actually matters. It skips the desperation, the pure human stubbornness, the last-second calls made under pressure, the slow, grinding erosion of a dying machine, and the one question nobody at NASA's been able to fully answer yet. When Voyager 1's final signal finally goes dark sometime in the 2030s, what exactly is humanity going to lose? To get what's going on right now, in the summer of 2026, you gotta rewind all the way back to the start. Not because the origin story is poetic, though NGL, it kinda is, but because that's the only real way to measure just how massive this ending actually is. September 5th, 1977, a spacecraft roughly the size of a small car gets launched out of Cape Canaveral, Florida, strapped to a Titan Centaur rocket aimed dead on at the outer solar system. The original mission brief? 5 years. 5 years of data, 5 years of planetary flybys. Then the mission gets called complete and everybody moves on. The engineers who built it, the scientists who loaded it up with instruments, the officials who signed off on the budget. Every single one of them was thinking 5-year project. Not one person in that whole room was thinking about what this thing might still be doing 49 years later. But here's where the first layer peels back. Voyager 1 wasn't even built for the journey it ended up actually taking. It was built for Jupiter and Saturn. That was the whole assignment. Swing past Jupiter, gather intel on the gas giant and its moons, cruise onto Saturn, document the ring system, wrap it up, done. And the spacecraft did exactly that. It swept past Jupiter in March 1979, catching volcanic activity happening on the moon Io that no telescope back on Earth had ever caught. It photographed Jupiter's swirling storm systems with a clarity so sharp it rewrote entire textbooks. Then it hit Saturn in November 1980, delivering the closest, most detailed images of Saturn's rings that humanity had ever laid eyes on. And then, technically, the primary mission was over. Voyager 1 had done exactly what it was sent out there to do. Sit with that for a second. The mission was complete in 1980. Everything that's happened since, every discovery, every single data point, every instrument reading, fired across the void, all of that has just been bonus content, extended mission. But extended doesn't even begin to cover 45 more years of nonstop continuous operation. That's not an extension. That's a whole entirely different story being written by a machine that was never designed to write it in the first place. What happened next is the part most coverage skips because it doesn't fit neatly into one clean headline. After the Saturn flyby, Voyager 1's cameras were still up and running. The spacecraft was racing outward into the deep solar system, hauling away from the sun at roughly 38,000 dim-arc. Mission planners started asking each other what to actually do with those cameras, instruments that still worked fine but had 0 planned targets left ahead of them. And that's exactly where one single scientist changed everything. Carl Sagan, part of the Voyager imaging team, had been holding on to an idea since 1980. He believed that before those cameras got powered off for good, Voyager 1 should turn itself around and snap one final photograph. Not of some planet it had never been to, not of a distant nebula. He wanted the spacecraft to photograph home. He wanted a picture of Earth, taken from the edge of the solar system. And almost nobody at NASA was with him on it. There were legit technical objections. Pointing the camera that close to the sun's direction risked frying the imaging system permanently. There were budget objections. There were scheduling headaches. For nearly a full decade, the idea just sat there in limbo while Voyager 1 kept cruising outward. It took all the way until 1989, 9 years after Sagan first pitched it, for NASA to finally sign off on the photo. And even then, it only happened because Richard Truly, NASA's administrator at the time, personally stepped in to make sure it actually got done before those cameras went dark for good. February 14th, 1990. The command gets sent. Voyager 1 warms its cameras up one final time and starts photographing the solar system for the last time ever. It captures 6 planets: Neptune, Uranus, Saturn, Jupiter, Earth, and Venus. Mercury and Mars got swallowed up in the sun's glare. Whole sequence, 60 images total. But buried in that batch was one single frame that would go on to become arguably the most philosophically heavy photograph ever taken. Camera pointed toward Earth. And from 3.7 billion miles away, Earth showed up as a tiny pale blue dot, just floating there in a stray scatter of reflected sunlight. Every human being who's ever lived, every civilization ever raised up, every war ever fought, every song ever written, every act of love and cruelty and pure genius in the entire span of recorded human history, all of it, every bit of it, squeezed into 0.12 of a single pixel, not even a whole pixel, a fraction of one. And 34 minutes after that image got taken, Voyager 1 shut its cameras off forever. That's the detail that makes your stomach drop. Not the photo itself, though the photo's genuinely incredible, it's the timing. That entire 60 photo sequence, pale blue dot included, wrapped up in the literal final window before the cameras got cut off permanently. If Carl Sagan hadn't spent 9 years fighting tooth and nail for that photograph, if Richard Truly hadn't stepped in at that last possible moment, if that command had landed just 35 minutes later, those cameras go dark without ever once looking back. The most famous image in the history of space exploration was 34 minutes away from never existing at all. But here's where it gets even heavier. Here's where the real story of 2026 actually kicks off. Because the cameras shutting off wasn't the end of Voyager 1, it was barely the middle. After the cameras went dark in February 1990, Voyager 1 just kept going, kept transmitting data. Its other instruments, 10 sets total, measuring everything from cosmic rays to plasma waves to magnetic fields, kept right on operating as the spacecraft pushed deeper and deeper into the outer solar system, and eventually straight past it entirely. August 2012. Voyager 1 crosses the heliopause, the boundary where the sun's magnetic field and charged particles finally give way to true interstellar space. It becomes the first human-made object in all of history to leave the solar system. The solar system. The entire sun-governed bubble containing every planet, every moon, every asteroid, every comet humanity's ever laid eyes on, Voyager 1 crossed clean out of all of it, and it was still transmitting the whole time. What most people aren't clocking is just how unprecedented that actually is. Voyager 1 is the only operational spacecraft that exists out there in interstellar space. Not one of two, not one of several. The only one. Along with its twin, Voyager 2, which crossed the heliopause in 2018 on a totally different trajectory, these two machines are giving us the only direct, in-place measurements of the space between star systems that exist. Not telescope guesses, not math models. Actual real readings from actual instruments physically sitting out there in interstellar space. No replacement satellite waiting in orbit. No follow-up mission already on the way. No backup at all. When these machines finally go silent, that whole window of direct measurement slams shut. Maybe for decades. And that window is closing right now. This is what's actually gone down this year in 2026, and this is what you need to understand about where Voyager 1 currently stands. The spacecraft runs off a radioisotope thermoelectric generator. Basically a device that turns heat from decaying plutonium straight into electricity. No solar power involved. Can't be recharged, period. That plutonium's been slowly decaying since 1977, and that decay is costing the mission roughly 4 watts of electricity every single year. 4 watts sounds like nothing. On Earth, 4 watts is a nightlight. On Voyager 1, 4 watts is the whole difference between a science instrument staying alive or going permanently dark. The shutdown plan's been years in the making. NASA didn't just stumble into this moment unprepared. The Voyager science and engineering teams sat down together way before the crisis hit and agreed on the exact order instruments would get powered off. A deliberate triage built to preserve the most scientifically valuable stuff for as long as humanly possible. Of the 10 instrument sets each Voyager launched with, 7 are already shut down. 7. What's left on Voyager 1 as of July 2026 is just 2 science instruments. The magnetometer, which reads the magnetic field around the spacecraft, and the plasma wave subsystem, which picks up on plasma oscillations and helps map out the density and behavior of the ionized gas Voyagers traveling through. Everything else is gone. Cameras got powered off first, back in February 1990. The planetary instruments, the ultraviolet spectrometer, the infrared instrument, all got switched off in the years after that. The cosmic ray subsystem got shut down on February 25th, 2025. Most recently, on April 17th, 2026, NASA fired off a command that took 23 hours to reach the spacecraft. That command deactivated Voyager 1's low-energy charged particles experiment, the LECP, an instrument that had been running almost nonstop since the actual day of launch in 1977. The LECP had been measuring ions, electrons, and cosmic rays from both the solar system and the galaxy beyond it for nearly 49 straight years without a single interruption. When that shutdown command executed, the LECP just went dark. Read that again. An instrument that ran for 49 years just went offline permanently. Not because it broke, not because it failed, because there's now so few watts left available that keeping it alive would have put the remaining instruments at risk. According to Karim Badruddin, the Voyager mission manager over at NASA's Jet Propulsion Laboratory, the call got made after a routine roll maneuver in late February 2026 caused a power level drop that nearly tripped the spacecraft's undervoltage fault protection system, the safety net designed to shut everything down and force Voyager into protective safe mode. They came within a hair of losing control of the entire spacecraft. Shutting off the LECP is what pulled them back from that edge. And this is where the whole thing flips, because what's left now isn't some failing spacecraft stumbling helplessly toward silence. What's left is a deliberately engineered survival mission. 2 instruments remain, and both of them happen to be among the most scientifically critical tools Voyager could possibly still have for the environment it's currently sitting in. The magnetometer's out there reading magnetic field conditions in interstellar space, data no other operating instrument anywhere else can replicate. But the engineers aren't just sitting back watching the power drain away. There's an actual plan, an aggressive, high-risk move the Voyager team's unofficially nicknamed the Big Bang. A coordinated overhaul of the spacecraft's powered components, swapping several systems out simultaneously for lower power alternatives in one tightly compressed operation. If it works, it could free up enough electricity not just to stretch out the mission's operational life, but potentially, and this is the part that still sounds almost impossible, to bring the LECP instrument back online after it just got shut off. The Big Bang is getting tested on Voyager 2 first, since it's got slightly more power to spare and sits marginally closer to Earth, making it the safer test subject. Tests were scheduled for May and June of 2026. If those tests come through, NASA's planning to attempt the same procedure on Voyager 1 no sooner than July of this year. The outcome's not guaranteed, though. Nothing about this mission has ever been guaranteed. Meanwhile, Voyager 1 just keeps moving. It's currently about 15.8 billion miles from Earth, 25 billion kilometers, and that distance keeps growing by roughly 38,000 miles every single hour. On November 18th, 2026, it's going to hit a milestone no human artifact has ever crossed before, exactly 1 light day from Earth. That means the electromagnetic signal Voyager 1 sends out, a signal so faint it arrives on Earth weaker than the power of a fridge light bulb, is going to take a full 24 hours traveling at the speed of light before it even reaches the deep space network antennas waiting to catch it. 1 full day of travel at 186,000 miles per second, just to cover the distance from a machine humanity launched to the very planet that built it. The antennas themselves are part of a story that doesn't get nearly enough attention. Deep Space Station 43 in Canberra, Australia, is the only ground antenna on the entire planet capable of sending commands to both Voyager 1 and Voyager 2. No other station has that capability, period. Between May 2025 and February 2026, that antenna was completely offline for major structural upgrades, with only a few limited operational windows available in August and December 2025. For the better part of 9 whole months, humanity's ability to send new commands to the most distant spacecraft it's ever built was severely locked down. The fragility of the whole chain connecting Earth to Voyager is easy to overlook, until you realize a single antenna upgrade schedule can decide whether engineers get to step in during a crisis, or just watch it play out helplessly. There's another dimension to this whole story that barely surfaces in mainstream coverage. Bolted to the outside of Voyager 1, and its twin Voyager 2, is a gold-plated copper disc, 12 inches across, carrying 115 photographs, a whole range of scientific diagrams, audio recordings of music from across every corner of human culture, nature sounds, and greetings recorded in 55 different human languages. This is the Golden Record, curated by Carl Sagan and his team. It wasn't designed for any audience alive today. It was built for whatever intelligence might intercept the spacecraft tens of thousands of years down the line. In roughly 172 years, a figure that's not a wild guess, but an actual astronomically calculated trajectory, Voyager 1 is going to pass within 1.7 light years of some small, obscure star sitting in the constellation Ursa Minor. Whether anything's even out there to receive the disk? Unknown. Whether the disk even survives that journey in readable condition? Uncertain. But it got launched anyway, because Carl Sagan genuinely believed the act of sending a message mattered, even without any guarantee there'd ever be a recipient on the other end. The spacecraft carrying that record into deep time right now is running on 2 instruments and an engineering transmitter powered by the radioactive decay of plutonium that got loaded onto the vehicle 49 years ago. This isn't chaos. This is the endpoint of extraordinary longevity crashing headfirst into the inexorable math of power loss. What makes this current moment different from every single previous moment in Voyager 1's long history is finality. For decades, every shutdown could get framed as a trade-off. Lose one instrument, gain more time for the others. But the instrument inventory's gotten so thin now that every shutdown from here on out isn't a trade anymore. Every single one is a subtraction with zero replacement. When the magnetometer eventually goes dark, there'll be no remaining instrument left to cover what it was measuring. When the plasma wave subsystem finally stops transmitting, the acoustic picture of interstellar space that only Voyager 1 could ever paint goes permanently silent. The engineers over at JPL say they're hoping to keep at least one science instrument running on each Voyager into the 2030s. But they're also quick to say, and this part matters a lot, that unforeseen problems could tank that timeline at literally any moment. An unexpected thruster failure, an electronics fault in a computer running 8,000 instructions a second out in an environment where no repair mission could ever reach it. A power drop that trips fault protection before any command from Earth even has time to intervene. And once an instrument shuts off permanently on Voyager 1, the heaters, keeping its electronics above catastrophic temperature limits, shut off right along with it. Out in the absolute cold of interstellar space, the components just freeze. They don't fail in some dramatic blowout, they just quietly go inert. No restart procedure exists, no recovery is possible. Hardware that took measurements no other probe could ever replicate just sits there, frozen and silent, drifting outward at 38,100 amperes into a darkness where it'll keep drifting for way longer than recorded human civilization's even been around. The signal coming back from Voyager 1 these days is already a ghost of what it used to be. A transmitter putting out roughly 22 watts, less power than a standard light bulb, firing information across 15 billion miles of empty space. By the time that signal actually reaches the deep space network antennas, its power is spread out across a sphere so massive that the energy actually landing on the receiving dish gets measured in fractions of a trillionth of a watt. Engineers have to filter it straight out of background noise using some of the most sensitive radio receivers ever built. That's what all these instrument shutdowns are buying. The continuation of that whisper for a few more years, coming from a place nothing else humanity's ever built has managed to reach. Former Voyager project manager John Cassani put it plainly in a 2024 NASA statement. They didn't design these things to last 30 years or 40 years. They designed them not to fail. Nearly 50 years in, that design's still holding up. But the physics is winning. That plutonium's going to keep decaying. That 4-watt annual loss is going to keep piling up, no exceptions. The decision tree engineers have been following for years now. Which instrument to sacrifice next, which system to protect just a little longer, is eventually going to hit its final branch. When that last instrument finally powers down, Voyager 1 isn't going to vanish instantly. The transmitter and onboard computers might keep running for some additional time after that, sending back basic engineering data, the spacecraft equivalent of a pulse with nothing left to actually say scientifically. The deep space network's going to keep listening the whole time. Eventually, that signal, too, is going to fall below the threshold of what we can even detect, or the power's just going to drop below the minimum needed to keep transmitting at all. And then, silence. Not the silence of failure, the silence of completion. Of a machine that got asked to run for 5 years and instead spent nearly half a century doing science in places no human instrument had ever reached, surviving computer failures and thruster degradation and power crises, and the cold, unforgiving math of radioactive decay. And then, finally, quietly, running out of the last few watts it needed to keep speaking. So what does all this actually mean for humanity? The real story here isn't the spacecraft. The real story is what we're going to lose when it finally goes quiet, and what that loss says about where we actually stand in relation to the universe around us. Right now, in the summer of 2026, the 2 Voyager probes represent the only direct sensing capability humanity's got past the edge of the solar system. No missions currently en route to replace them. No probes scheduled to reach interstellar space within the next 20 to 30 years. The data the magnetometer and plasma wave subsystem are sending back, live readings from actual interstellar space in real time, straight from instruments physically immersed in that environment, isn't going to be available again from any new spacecraft for a whole generation, maybe more. So every single day those 2 remaining instruments keep transmitting is a day that's genuinely irreplaceable. Every reading is a measurement that can't ever be taken again, because the machine taking it is sliding further and further into a void it can never come back from. Somewhere out past 15 billion miles of darkness, a small golden record is bolted to the outside of a dying spacecraft. It's carrying photographs of a sunrise, of a mother nursing her baby, of the UN building lit up at night, images Carl Sagan and his colleagues hand-picked as representative of what humanity actually is. It's carrying music. It's carrying the sounds of wind and rain and thunder and ocean surf. It's carrying greetings in 55 different languages. In 40,000 years, it might drift close enough to a star that something could theoretically stumble across it. But way before that happens, maybe within a few years, maybe by the end of this decade, the spacecraft carrying it is going to stop transmitting entirely. The instruments are going to go dark, one after another. The signal's going to fade out. And what was once the most distant conversation humanity's ever maintained is simply going to end. The question that lingers, the one NASA still can't fully answer, the one the engineers at JPL live with every single day they sit down to manage those final few watts, is whether this ending represents an achievement or a warning. Is Voyager 1 proof that human engineering can outlast its own expectations by a whole order of magnitude? Or is it a reminder that in a universe this massive, even our most extraordinary reach, 15 billion miles, 49 years of continuous operation, crossing clean out past the boundary of interstellar space itself, still amounts to less than a single step on an infinite road? The Big Bang fix is being tested right now, this very moment. The magnetometer's still reading, the plasma wave subsystem's still listening, the signal's still arriving at Earth after its 23-hour journey across the void. But the power's still dropping, 4 watts every year, without exception, without pause, without any possibility of reversal. And somewhere buried in that arithmetic is the answer to a question nobody really wants to ask out loud. How much time does humanity's furthest outpost actually have left? The mission managers are hoping for the 2030s. The physics is going to have the final word. And when that final word finally comes, it's not going to arrive as some dramatic announcement. It's going to arrive as silence, the universe's oldest and most absolute response to everything humanity has ever sent out into it.